Moment of inertia. It is the measurement of the resistance of a body to a change in its rotational motion. That is, it is the measurement of rotational inertia. Moment of inertia of a single particle. Consider this is a rotation action. A single particle of mass m is revolving around it, and the distance from the rotation axis is r. Then moment of inertia of single particle about this axis will be given as I equals to mr square, where m is the mass of the particle and r is the perpendicular distance from rotation axis. Unit of moment of inertia will be kilogram meter square and dimensional formula ml2. Moment of inertia of a system of particles or a rigid body. Consider a rigid body in which different particles have different position and the mass are different of different particles, and their distance from rotation axis is r1, r2, r3, r4 dash 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 dash. For the ith particle it is ri, and the mass of ith particle is mi. The moment of inertia of a system of particles about an axis is given by I equal to sigma I mi ri square, where ri is the perpendicular distance from the axis to the ith particle which has a mass mi. Derivation. Consider a rigid body. This is a rigid body, and in which a ith particle is at a distance ri from the rotation axis, and the mass of particle is mi. Consider a rigid body is rotating about an axis with constant angular velocity omega. Consider ith particle of the rigid body at a perpendicular distance ri from the axis. All the particles in rigid body rotates with same angular velocity omega. The linear velocity of ith particle is Vi equals to Ri omega. Hence kinetic energy of the ith particle Ki equals to 1 by 2 mi Vi square equals to 1 by 2 mi Ri square omega square, because Vi equals to Ri omega, or equals to 1 by 2 mi Ri square into omega square. Hence kinetic energy of rigid body K equals to sigma Ki equals to sigma 1 by 2 mi ri square into omega square equals to 1 by 2 omega square sigma mi ri square equals to 1 by 2 omega square I, or equals to 1 by 2 I omega square, where I equals to sigma mi ri square is the moment of inertia of the rigid body. For continuous mass distribution, we replace the summation by integration. Thus, I equals to integration r square dm. Here, this is the situation. So, this body is rotating about this axis, and a elementary mass dm is taken at a distance r. Then, and this mass is continuous, so we can use directly moment of inertia I equals to integration r square dm. For example, here two two masses are separated by a distance L of light rod, and it is rotating about an axis passing through midpoint of the rod, and the mass of this point is m by 2 and this point is m by 2, and the rod is massless. Then moment of inertia will be sigma I equal to sigma mi into ri square equals to m1 r1 square plus m2 r2 square. Here m1 is equal to m by 2 and r1 equals to l by 2, because from this axis the distance is l by 2 of this body, and similarly of this particle is l by 2. So m1 is equal to m by 2, r1 is equal to l by 2, m2 is equal to m by 2, and r2 is equal to l by 2. Putting hence I equals to m by 2 l by 2 का होल स्क्वायर प्लस m by 2 l by 2 का होल स्क्वायर. सोल्विंग we get m by 2 into 2l square by 4 equals to ml square by 4. So the answer. Now example, consider a ring of mass m is rotating about its axis passing through the plane from the center of the ring. Then what will be its moment of inertia? We have to calculate the moment of inertia. To calculate its moment of inertia, consider a elementary length dl of mass dm. That is this. This is a small length of this circumference part of ring. We have linear mass density will be given as lambda equals to m by 2 pi r. Hence elemental mass dm will be lambda into dl equals to m by 2 pi r into dl. Hence elementary moment of inertia, that is moment of inertia of this part, di equals to dm into r square, because distance is r from the rotating axis, or equals to m by 2 pi r dl into r square equals to mr by 2 pi into dl. Hence moment of inertia I equals to integration di or integration 0 to 2 pi r mr by 2 pi into dl, or equals to mr by 2 pi. Integration of dl is l, but limit is 0 to 2 pi r. So mr by 2 pi into 2 pi r equals to mr square. Thus the moment of inertia of a ring of mass m about an axis passing through the center of the ring and perpendicular to the plane of ring is mr square. Now theorem of perpendicular axis theorem. The moment of inertia of a planar body lamina about an axis perpendicular to its plane is equal to the sum of its moment of inertia about two perpendicular axes concurrent with the perpendicular axis lying in the plane of the body. Here the situation is shown. Consider a rigid body is here shown. Here consider now we have, this is a rigid laminar planar body, and a axis is passing through z, that is perpendicular to the plane, and this body is lying in the xy plane, that is xy plane. Now we take a ith particle of mass mi at a distance ri from the origin, and its yi distance is from x axis, and xi distance is from xi distance is from z axis. Now because ri square equal to xi square plus yi square, it is shown in the figure, that is xi distance is from y axis, and yi distance is from x axis. Now moment of inertia of the ith particle about x axis will be mi into yi square, and moment of inertia of laminar body about x axis ix equal to sigma I equals to n mi yi square, equation 1. Moment of inertia of ith particle about y axis mi into xi square. Hence moment of inertia of laminar body about y axis iy equal to sigma I equals to 1 to n mi xi square. We are considered there n particles. Now moment of inertia of ith particle about z axis. Z axis is mi into ri square, and equals to mi into xi square plus yi square, because ri square is xi square plus yi square. Hence moment of inertia of laminar body about z axis iz equals to sigma I equals to 1 to n mi ri square equals to sigma I equals to 1 to n mi into xi square plus yi square equals to sigma I equals to 1 to n mi xi square plus sigma I equals to 1 to n mi xi square. And now this represents the moment of inertia about x axis, and this represents the moment of inertia about y axis of the laminar body. So iz equals to ix plus iy. Hence we can say that iz equals to ix plus iy, where iz is the moment of inertia of the body, laminar body about z axis which is passing perpendicular to the body, mm, perpendicular to the plane of the body, and ix is the moment of inertia of the body along a line in the plane, and iy is also a moment of inertia of the body along a line which is perpendicular to the x and line in the plane. So this is the theorem of perpendicular axis theorem. Note: find moment of inertia of circular ring about diameter. Here it is, a circular ring is given which is placed in the xy plane, and we have to find the moment of inertia about its any diameter. Now we know that Iz is equal to mr square. Now from perpendicular axis theorem, Iz equals to Ix plus Iy, because Iz z axis is passing through its diameter. Also z axis is also passing, and y axis is also passing through its diameter. So we can write Ix as Id and Iy equals to Id, or equals to 2Id, moment of inertia of diameter, about diameter, and 2Ids. This implies Id equals to Iz by 2 equals to mr square by 2 1 by 2 mr square. Example 2, moment of inertia of disk about diameter. Now we know that the moment of inertia of a disk about z axis, if disk is placed in xy plane, then its moment of inertia about z axis, that is z axis perpendicular to its plane, Iz equals to mr square by 2. Perpendicular axis theorem, we now get Iz equal to Ix plus Iy equals to Id plus Id equals to 2Id, where Ix Iy equal to Id, that is moment of inertia about diameter. This implies Id equals to Iz by 2 equals to 1 by 2 into mr square by 2 equals to mr square by 4. Now parallel axis theorem. The moment of inertia of a body about any axis is equal to the sum of the moment of inertia of the body about a parallel axis passing through its center of mass, and the product of its mass and the square of the distance between the two parallel axes. Here the situation is shown, that is we are considering any axis, that is z axis, j axis, which is passing through at any point in the body, and we have to calculate the moment of inertia. Then the moment of inertia about the axis will be equal to the moment of inertia about the axis passing through the center of mass, and mass of the body multiplied by distance, square of distance between these two axes. Let Iz equal to ICM, that is center of mass. Moment of this represents a moment of inertia about z axis, and z axis is passing through the center of mass, we are assuming. So ICM is representing the moment of inertia about center of mass. So moment of inertia of body about a axis which passes through CM. Now Iz equals to ICM equals to sigma MIRS square. We know that from formula MIXI square, because ith particle is at xi distance, and z dash axis is at a distance. So this distance will be xi minus a. Equation 1. Again, moment of inertia about this ith particle, about this z dash axis is mass into this distance square. So we have Iz dash equal to sigma mi xi minus a whole square equal to sigma mi into xi square minus 2xi into a plus a square. equal to sigma mi xi square minus 2a into sigma mi xi plus sigma mi a square equal to sigma mi xi square minus 2a into 0, because this term will be 0, because if we take one distance at in this side, there's another distance will be in this side, and this will give 0 plus a square into sigma mi, or equals to, because this represents the moment of inertia of the particle about z, so summation will give the whole moment of inertia of whole body about z axis, so it is iz plus a square, and this will summate, this summation will give the whole mass of the body, so a square into m, thus iz dash equal to icm plus ma square. This is the parallel axis theorem. Based on this theorem, let us consider some example. Now, let us consider moment of inertia of a rod of mass m and length l, about its axis passing through its center or center of mass. If the mass of rod is m and length is l, then linear mass density will be given as lambda equals to m by l. Now consider a thickness, a mass of thickness, a part of this rod of length dx thickness, and its mass is dm, then dm will be equal to lambda dx equal to m by l into dx. So moment of inertia of this elementary part about this axis will be mass of this part into x square. So di equals to dm into x square, hence I equals to integration di integration x square dm. Now we have to take limit, because one part will be at this, and this elementary mass can be varied from here to here, so from minus l by 2 to l by 2, so we are written here minus l by 2 to l by 2 x square m by l dx, or m by l is constant, so we come out of the integration m by l minus l by 2 to l by 2 x square dm m by l. Now this integration will be x cube by 3, so x cube by 3, and limit is minus l by 2 to l by 2. Solving this, putting the value m by tl l by 2 chi l cube minus l by 2 chi l cube equals to m by 3l l cube by 8 plus l cube by 8 equals to m by 3l l cube plus l cube by 8, m by 3l 2l cube by 8, m by 3l into l cube by 4, ml square by 4 equals to 1 by 12 ml square. Now another example. Consider we have to find the moment of inertia of the rod, a rod of length L and mass M, about a axis which is passing through its one of the end, that is from this end or here this end. Then what will we have to do? We will simply apply the parallel axis theorem. First we calculate the moment of inertia about its Cm, which we have calculated earlier, 1 by 12 ml square, and using the parallel axis theorem we can calculate about this axis. Now IPQ, that is which is PQ, about the moment of inertia about PQ axis, which is PQ axis is passing through center of mass, so this will be IPQ will be ICM equals to ml square by 2, we have earlier calculated. Now using parallel axis theorem, we have IZZ dash, that is moment of inertia about this axis, ZZ axis will be moment of inertia about this axis, plus mass of rod multiplied by distance between, square of distance between the axis. So here we have written from parallel axis from IZ dash equals to ICM plus M into A square, or ml square by 12. We have calculated it earlier, plus m into. Now a is L by 2, so L by 2 the whole square. ml square by 12 plus ml square by 4, ml square plus 3 ml square by 12, 4 ml square by 12 plus ml square by 3. So moment of inertia of a rod will be uh, moment of inertia of a rod of one of its end will be ml square by 3. This is the another example. This is a disc, laminar disc. Uh, Now we know that one of its diameter, the moment of inertia is mr square by 2. Now from applying parallel axis, we have to calculate about its tangent. So I tangent will be I diameter plus mr square. Mr square by 2 plus mr square by 3 equals to 3 mr square by 2. Now radius of gyration. It is defined as the effective distance from the axis where the whole mass can be assumed to be concentrated so that moment of inertia remains the same. Thus I equals to m into k square, where k is called the radius of gyration, or k equal to root under I by m. Consider a z axis. Now, if we want to calculate the moment of inertia of this body, then this body may be considered at it is concentrated at a point mass like this, and it is from k distance from the that z axis, and then the moment of inertia will be I into mk square. Kinematics of rotational motion about a fixed axis. Here a rigid body is shown, and z is a axis. Also, this is y dash, and this is x dash axis. Now the kinematical equation for rotational motion with uniform accelerations are omega equals to omega naught plus alpha t, where omega is the angular velocity, final angular velocity, and omega naught is the initial angular velocity. Alpha is acceleration, angular acceleration, t is the time, and theta equal to theta naught plus omega naught t plus 1 by 2 alpha t square, where theta is the final position of the angular position of the body, theta 0 is the, or theta naught is the initial angular position, omega 0 is the initial angular velocity, and alpha is the angular acceleration of the body, t is the time interval, and omega square equals to omega naught square plus 2 alpha into theta minus theta naught, or equals to omega square plus 2 alpha into delta theta, where omega naught initial angular velocity, omega final angular velocity, alpha angular acceleration, theta final displacement, theta naught equal to initial displacement. We have for linear motion v equal to u plus at, x equals to x naught plus ut plus half at square, and v square equal to u square plus 2a into x minus x, u square plus 2as. Now we know that if a body is revolving around any point and it takes t time, then it revolves 2 pi radian angle in time t. So angular velocity of that particle will be omega equal to 2 pi t, and 2 pi f is the linear frequency, where 1 by t equals to f, and f is the linear frequency. Since in time interval t one rotation is considered, then 1 second there will be 1 by t rotation, and this is called frequency. So f equals to 1 by t. Rotation per second is called frequency, rps, or omega equals to 2 pi by t equals to 2 pi into 1 by t equals to 2 pi f. Example, for f equal to 5 rps, that is 5 rotation per second, then omega will be 2 pi f, 2 pi into 5 radian per second equals to 10 pi radian per second. Now rps equal to rotation per second. This can be written as rotation divided by, because second can be converted into minute, so 1 by 60 minutes equals to 60 rotation per minute. So 1 rps will be equal to 60 rpm, hence 1 rps will be equals to 60 rpm, or 1 rpm equals to 1 by 60 rps.